Hello, my name is Yuan. I'm a PhD student at Chalmers University of Technology. Today, my topic is about machine learning enables high quality and high throughput prediction of essential genes. So firstly, what are genes? Genes play an important role in determining physical traits. They carry information that makes you who you are and what you look like. For example, whether your hair is curly or straight, whether your leg is long or short. This is basically a picture of genes. And what are essential genes? Essential genes are those genes that are critical for the survival of an organism. Because deletion of essential genes can cause the death of an organism. So understanding essential genes could provide targets for new antimicrobial or antibiotic drugs. And it is also very useful for minimal genome design. However, the identification of essential genes via wildlife experiments is labor-intensive, expensive, and time-consuming. Therefore, computational methods for predicting essential genes are therefore urgently needed. For example, machine learning. For machine learning, the first step that we need to do is to have a lot of data for training. So here we collected more than 10,000 entries about gene essentiality data from these five species based on peer-reviewed literature or open source databases. So then we developed our machine learning workflow for essential gene prediction using machine learning. In the workflow, we mainly calculated sequence features and evolution-based features. So for all of the genes in these five species, we calculated sequence features and evolution-based features one by one. And after that, we can have a big matrix. So then we applied some kind of traditional machine learning algorithms for the prediction of gene essentiality. And then we can know whether the gene is essential or non-essential. One more important thing is about feature analysis in machine learning, because in this step, if we do feature analysis, we can know whether some features could differentiate essential genes or non-essential genes or not. So for example, here, the y-axis in the three box plots is features, various features, and the x-axis is the species. Using this box plot as an example, when checking the median value of gene occurrence, we can find that the essential genes have relatively higher gene occurrence number compared with that in non-essential genes. And in another four species, it is also like that. So we can conclude that gene occurrence number could differentiate non-essential genes and essential genes. Of course, for conservation score and the number of average paradox, we can also conclude the same conclusion. Of course, for DM protease, it is the same trend. The median of, value of DM protease for essential genes is much lower than that in non-essential genes. So after that, we construct the machine learning workflow and develop the machine learning model. Another thing is the machine learning performance. So here, we integrated sequence features and evolution-based features. We got an AUC value as 0.91. By using sequence features alone, the AUC value is 0.68. So what is the AUC value? It is the most important parameter to evaluate the machine learning performance. The higher the AUC value, the better the performance of the machine learning model. So then we can have a high AUC value. So we can know that it is really good for our machine learning model. And then we also evaluated the feature importance. In this figure, we shoot 5 top features contributing to essential gene prediction. So the top 3 are evolution-based features, and another 2 is sequence features. Here we call it KMOR, PGA or KMOR, GAA. That is 3 nucleotide sequence fragments. And the features with lower importance are not shown. On testing dataset, we can also have the same conclusion. Here we mainly applied the SVM machine learning model and the random forest machine learning model to evaluate the performance on testing dataset. We can notice the improved AUC value for essential gene prediction by using sequence and evolution-based features. Okay, and then when talking the case applications, we applied the machine learning model to predict essential genes for all 332 yeast species, which is reported in another paper. And in this paper, they reported 332 sequenced budding yeasts. And the prediction results were stored on Figshare, which is an online repository free to access. So this provides a valuable resource for further studies in the yeast research community. Okay, finally, let's give a final summary. In this presentation, the identification of essential genes via wildlife experiments is time-consuming, expensive. So computational methods for predicting essential genes are therefore urgently needed. And then we developed a machine learning approach to predict essential genes. We also found that by integrating evolution-based features, gene essentiality prediction could be improved. And then we finally applied the model into 332 yeast species, which is a relatively good resource for the yeast community. Okay, thanks for your listening. Thank you so much.